Is February, March 2024, paper 42. Let's start with this. So this is P42. So the first question is, explain why the gravitational potential near to the point mass is negative. This is a repeated question. You should memorize its marking scheme. And you will find this question many times. So basically what happens is, in physics, we say that any work done by an attractive force will be considered to be negative. Now, if you look at a surface of any planet, and if you allow a mass to fall down on it, that means that the gravitational attraction that the mass already provided to the other mass has done some work in bringing this mass closer to itself. This inherently causes a negative sign because the system has done some work for you, or the system has done this work on its own. So in order to explain this to the examiner, that why this is negative, first you will say that the potential at infinite distance is 0, right? According to the formula of Gm divided by R. If you increase R to an infinite value, the answer is going to become 0. Now, as you come closer, it becomes negative. Why? Because work done by an attractive force is considered to be negative, right? On the other hand, how to explain it from a counterintuitive perspective? That would be that if you had to take this mass away from the object, you'll have to add energy into the system. So that will be a plus sign. Now, when you add energy into the system to carry it from this surface and away from that surface, you're adding energy into the system. Now, if you want to get that energy back, when you allow that object to fall down again, that will be considered as negative. So one way of saying this is that work done by an attractive force is negative. Another perspective would be energy or work must be done to carry objects away from a massive object, right? So it's as good as saying that if you added energy, that should be positive, and when you allow it to come back down again, when you allow it to act on its own, it will become negative, right? So there are two ways to say this. Okay, so this question in terms of graphical analysis is a bit different, because generally we're used to seeing the gravitational potential to look something like this. But what he has done, he has converted this R into 1 over R, so that this equation becomes a straight line, or this graph becomes a straight line. That's all the purpose that he wanted to do over here. You can read the question and then go about it. So I can see that this is for the potential. So I will remind myself that the potential's formula is negative Gm over R. Okay, and the unit is joules per kg. The question says, show that the mass of the planet is this. Now, I have explained before that in the questions of show that, if you're unable to find this answer, you can still use this value for the incoming parts. So don't lose hope, move to the next question. Now, if you want to show this, I can take the help from the graph. I can choose any random value from the graph. It's my choice, and I will find the value of mass. So the formula for potential, again, is equal to negative Gm divided by R, right? And I have the value of phi from the graph. I have the value of gravitational constant. This is what I want to find out. And I can find R as well. But we can see that in the graph, it's 1 over R. So let's write this down in a different way. So this is 1 over R into Gm. Now this looks more plausible. This looks acceptable because I have a value of 1 over R from the graph. What I have done is I've chosen a value from this 3, right? So you draw a dotted line with the help of the lead pencil and a ruler, and then you find out this value. You could have chosen any value. You could have chosen any other value. You could have chosen at 2, at 1.5, 1, so on and so forth. It does not matter, right? I chose this value because I can see that by counting method, this coordinate is exactly passing from a certain point. It's neither up or neither down. It's not in between. It's exactly at this point. So that is why I'm choosing this point. So then simply replacing the values, this comes out as 1.76 into 10 raised to the power 8 equals to. Now no need to worry about this negative sign because we can see that the graph value is also negative. This is also 1. This is also negative 1.76, right? So this negative and this negative of the formula gets cancelled out eventually. That's why I'm not mentioning this. Okay. All right. So then we have gravitational constant, which is 6.67 into 10 raised to the power minus 34 into the mass of the planet, which we don't know, divided by the value of radius. Now we don't have the radius in division. What we have is a factor of 1 over r being multiplied. So the place at which this value is found is this. So 1 over r already has this value. I don't have to do it. So this will be multiplied by 3 into 10 raised to the power minus 6. Sorry, minus 8. Yeah. So when you take these factors to the other side, they're going to get divided, and m comes out to be as 8.795 into 10 raised to the power 25 kg, which up to two significant figures, as per my knowledge, is still 8.8 into 10 raised to the power 25. So effectively what we have done is we have shown that this can be achieved. Okay. Okay, so moving on to the next part. He says that the rotation of the planet is 0.72 Earth days. Okay, fine. The satellite is in orbit. Planet remains above the planet. So this is basically a geostationary satellite which stays above the surface of that planet. Use the mass in part B1. Again, you can see that he is asking you to use that value. If you are unable to show this, you can still use this value to solve the next part. Determine the radius r of the orbit of the satellite. I personally don't like these parts because the proof for this is a bit longer. But since it's a question, we have to solve this. So what is the logic behind this? You have to write this down for 1 mark. So gravitational attraction. I'm just writing the acronym. So gravity is providing the necessary centripetal force in order to do this. So the gravitational attraction is gmm over r square, and centripetal force is actually mr omega square. This could have been mv square over r, but since we're dealing with time period and everything else, so I know that omega is equal to 2 pi by t, so I will prefer that I use the equation for omega instead of using mv square over r. So right off the bat, we can see that the small mass of the satellite gets cancelled out, and this r goes to the other side. We are left with gm equals to r cube into omega square. Now since r is what is required, I'm going to make that the subject of the formula, and not before replacing this with 2 pi by t whole square. Taking all of these things to the other side, this comes down as r cube equals to t square with gm divided by 4 pi square. You can perform the necessary algebra. You will land at this equation. And then it is simple matter of replacing values. So r cube is equal to t square, which is 0.72 days, Earth days. So this will be 0.72 multiplied by 24 hours, multiplied by 3600, because we want to convert this into seconds, into gravitational constant, which is 6.67 into 10 raised to the power minus 34, multiplied by the mass of the planet, which was found in the previous part, 8.8 power 25. So this is 8.8 into 10 raised to the power 25, bracket close, divided by our 4 pi square. So this is 4 pi square. Don't forget to take the cube root on the other side. When you bring this to the other side, this is going to become third cube root of this whole equation, okay, from including the denominator as well. So this r comes out as 8.3 into 10 raised to the power 7 meters. This is 8.3 into 10 raised to the power 7 meters. Okay, this is a repeated question as well. This geostationary orbit. He says that the speed of the satellite is 8400. The mass is this. Determine the additional energy required. Additional energy. This is the key point. To push this satellite from orbit to infinity. Now, what's the situation? So this is the planet, for example. This is where the satellite resides right now. It is in geostationary orbit, rotating like this, above the surface of the Earth at a certain height. Okay, and the radius of orbit from the center is given to us as 8.7 power, 8.7 into 10 raised to power 7 meters. We know that it exists at this point. He says, what should I do so that this satellite eventually rolls out of its orbit, keeps circulating, and eventually goes so far ahead that I can consider this distance to be infinite. How much energy do we need to do this? Okay, so this is the target of the question. So first we need to understand how much energy the object already has. So object already has a kinetic energy, so I will simply write down energy or kinetic energy already possessed by the object is simply half into mass is 1200 and speed is 8400 squared. This comes out as 4.23 into 10 raised to power 10 joules. It already has this energy. Now in order to find out how much energy we do we need to get away from this point up to an infinite distance, we will have to use the equation for gravitational potential. So that would be energy needed in terms of simple gravitational potential. Now, previously what we used to do in O levels was simply use mgh to go to a certain height. But we can't do that in A levels. We have to use the sophisticated formula for potential, that is gm over r, then multiply with the mass that is being pulled away from the situation. So the formula goes change in potential multiplied by mass. So first we need to calculate the change in potential because mass is of the satellite. We are not concerned with that. It's not a problem. So change in potential. What is the final destination? So the final destination is infinity. At infinity, that becomes 0. Since we're looking for change calls for a negative sign, and the initial potential will be negative gm over r. So this negative and this negative cancels out. We are left with gm over r. Simple, right? And this r is this distance that was given to us or calculated by us in the previous parts. So let's calculate this. So this will be a change in potential multiplied by mass equals gm over r multiplied by mass, which is equal to 6.67 into 10 raised to the minus 34, mass of the planet 8.8 into 10 raised to the power 25 divided by r, distance at this point, right? So this is 8.7 into 10 raised to the power 7. All of this multiplied with the mass of the satellite, which is 1200 kilograms as given in the question. So in this space, this mass is being moved. So how much energy will that create? How much energy or gravitational potential energy is required to do so? So when you calculate this, your answer comes out as 8.4 into 10 raised to the power 10 joules. Now be advised, this is the energy that we need to go away, because the way this energy is calculated is simply by gravitational potential, that at infinity this energy was 0. If the object was allowed to fall down up to this point, how much energy will it have? By calculating mgh, it will have 8.4, right? So if I want to push it away, I still need to inject, I still need to give it back this much amount of energy so it can climb its levels and go up to an infinite distance. Now this is my requirement, this is my need for the system. Okay, now how do we do this? How much energy do we need to do extra? How much energy do we need to give extra? You see, the object already possesses this much amount of kinetic energy. So the object already has 4.23 into 10 raised to the power 10 joules of energy. Already it has this much amount in its pocket. So when we take the difference, we find out that only an additional 4.2 into 10 raised to the power 10 joules is needed. So the kinetic energy combined with this extra energy will lead to this 8.4 and collectively give us the answer or the necessary energy to go away up to a distance of infinite or up to an infinite distance. I understand that after subtracting this, your answer might not be 4.2, but whatever that answer is, you're going to write this down over here. So by my calculation, this is because I rounded off to 4.2 and missed out 3, but if you want to include this in this calculation, then that would be fine as well. So I need an extra 4.2 into 10 to the power 10 joules so that I can push the satellite from this point up to an infinite distance away from the mass. That is how much extra energy I need to supply. Question number 2 goes by referring to both kinetic energy and potential energy. Explain what is meant by internal energy of an ideal gas. Now for an ideal gas, there are no bonds being formed. When there are no bonds, the work done due to P delta V or the work done due to the bonds formation is actually equal to 0. Now the equation for internal energy, simply stating that it is the sum of kinetic energy plus potential energy. Are there any potential energy involved in the ideal gas? No, because potential energy is related to the number of bonds. Now, since this whole part becomes equal to 0 for an ideal gas, the change in internal energy is proportional only to change in kinetic energy, and we know that kinetic energy is proportional to temperature. So all of these things that I've mentioned, you have to write this down in terms of English, simple English. You can write down that for an ideal gas, the potential energy is 0. Hence, all the internal energy depends now on kinetic energy, and kinetic energy depends on the temperature of the substance. So whatever energy, whatever work done the ideal gas might or may not do will primarily be controlled by the temperature or heating of the gas. Alright, so the next question is said that we have a fixed mass of an ideal gas at a temperature, this one, and the piston is free to rotate or move. The initial volume is this much, and thermal energy, heating, is supplied, and the gas volume increases by this volume or this value. Please note that delta V is equal to V2 minus V1 equals to 5.20 into 10 raised to the power minus 5. This increases by means that it has already changed by this value, right? So this was one of the confusions that might cause trouble for you. And it is moving, or it is expanding as the volume increases. So it is a case of expansion, right? So an initial guess would be that it has to have a negative sign, right? But we will see that it will not be the case over here, right? So against the atmospheric pressure. So work done is equal to P delta V. The atmospheric pressure is 1.1 into 10 raised to the power 5. The change in volume, delta V, already given to us as 5.20 into 10 raised to the power minus 5. When you calculate this, this answer comes out as 5.25. Now previously we have done this as work done on the gas, then the expansion leads to a negative sign. But that was work done on the gas, right? In those situations, yes, there would be a negative sign, but since it is going to be a different perspective, that because this is work done by the gas, now on the gas and by the gas changes the sign, changes the perspective of this whole system. So over here, there will come a positive sign for this scenario, right? This will be positive 5.25. And just for the sake of understanding, although again in my previous lessons we have done that expansion causes a negative sign, but only when we say that this is work done on the gas, right? But if it is work done by the gas, then this perspective has to go to the opposite direction. Because let's discuss this. We have this table, this chart, in which you will find that a case of expansion in this question has led to a negative answer. Over here in February, March, the case of expansion has led to a positive answer. So why is there a difference in answer? Just because he asks a different question. In this question, he asks work done on the gas. So the expansion leads to a negative answer. And in this question, he's asking us work done by the gas. Now, if the work done is being by the gas, then what is the work done being on to? So work done by the gas on the atmospheric pressure. Since it is pushing away that atmospheric pressure, it has to do some work. So that will be a positive sign. That should be a positive sign. And when we say work done on the gas during expansion, then of course, who did work on the gas? The atmospheric pressure. So when you look at it from that perspective, that is going to give you a negative sign, because the gas has to take away energy from the system and give it to the atmospheric pressure. You can say use it to work, do work against the atmospheric pressure. So please, I'm going to clear this out. Notice how this word on and by changes the answer of expansion and compression. You can find an answer for compression with the positive sign when he says work done on the gas in this question as well. So far I don't have a question for this, but I'm sure that this table, if gives us the correct answers of writing down the signs, then of course we can find a question for this scenario as well. Okay, next step, he says calculate the final thermodynamic temperature. When he says thermodynamic temperature, it means he's talking about the Kelvin scale. So I will be ignoring this 20 degrees mentioned in the question, that is over here. I will convert this into Kelvin. Now, in order to do this, we have an equation that is PV equals to nRT. And then we have a simple answer that since the mass of the gas is fixed, the moles and the universal gas constant get cancelled out. So we understand that PV divided by T should be equal to a constant value. They should be constant, equal to the PV divided by T of another situation. They should be constant, because if P increases, V decreases, T increases, no matter what happens to these values, their answers should come out as equal from one situation to another. So P, we can see, also gets cancelled out because it's about the atmospheric pressure. Atmospheric pressure is not changing, so what we are left with? We are left with V1 divided by T1 equals to V2 divided by T2. So that is the equation that we are left with. So let's replace the values. So V1, the previous volume of the system, was 1.24 into 10 raised to the power minus 5 divided by the initial temperature was 273 plus 20 Kelvin scale converted. The second stage was the new volume. Now, be advised that it changed or increased by this value. The original volume was this. So the volume today will be an addition of these two. So 1.24 into 10 raised to the power minus 4, I think is that's minus 4 plus 5.2 into 10 raised to the power minus 5. This is the volume today divided by the temperature T, which we don't know today. When you calculate this, this comes out as 415.8 Kelvin, which will be 416 Kelvin. So yes, by adding thermal energy into the system, we did two things. Not only did the gas expanded, its thermal energy or its temperature increased from 293 Kelvin up to 416 Kelvin. Its temperature has increased, right? Okay. Where this 293 comes from, that is simply 273 plus 20. This was the previous temperature and 416 is the current temperature. He said the mass of the gas is this, 16 grams, expansion net transfer of 960 joules, the specific heat capacity, very easy question, so that will be Q equals to MC delta T. We've transferred 960 joules, mass is 16 grams, converted into kg by dividing by 1000 because there is a kg in the unit in the final unit. So C is what we want to find out. Then simply 416 minus 293, a delta T. So our C comes out as 487.8 joules per kg, right? So rounding this off to two significant figures, this becomes 490. The next question requires a bit of an understanding of the first law of thermodynamics, but let me give you a small brief summary of this equation. So this is an internal energy equals to change in Q plus change in W. Now this is my internal energy. This is responsibility of the heating effect, and this is the responsibility due to P delta V, or you can say due to the potential energy or the bonds formation, right? So for an ideal gas, what was our understanding? That this whole system becomes zero. But was it zero in this case? It should have been zero. That's why you will notice that this value is very, very small, right? It should have been zero ideally, but it's not. Anyways, moving on. So what's happening at this point? He says, use the first law of thermodynamics to predict when this happens, what happens. He says that now the system returns to its starting temperature, but the piston was not allowed to move. That if it was allowed to expand, let's say, then the current situation might look something like this. That if this was the piston at this location, under new circumstances, the piston might be at this location, which means that from the original perspective, it was allowed to expand. Now, once it has expanded, it was allowed to cool down, which means that its temperature came back from 416 Kelvin back to 293 Kelvin at room temperature. This is what happened, but now the syringe is still in the expansion position, right? Now he says that thermal energy is again provided to the system to increase the temperature. If that is done now at a larger volume, what will happen to its specific heat capacity? Now notice that since now the thermal energy that you provide is not going to translate into expansion of the gas, it is primarily linked to heating of the gas. Your thermal energy that you provide externally does not have to do two things at this time. It only has to do one thing, and that is to increase temperature. So when you provide the heating effect previously, let's say you provided 960 joules, out of that 960, some of that 5.3 joules were used to expand, and the remaining approximately 55 joules was added into the internal energy reserve. That was the original case. Today, since the volume is fixed, he says that the position of the piston is fixed, the P delta V equals 0 now, which means that according to this equation, delta U equals to delta Q heating plus delta W, this system becomes a 0. If you wanted to bring about the same change in the internal energy, which is 955, you would require a heating of 955, not 960, because now no extra energy is needed for expansion. So since you are requiring lesser energy as compared to before, your equation Q equals to MC delta T, you have a smaller answer of Q as opposed to previously you were using 960. You have to, or you're providing less energy for the same job. So since mass is not changing, delta T is not changing because you want to provide the same change. So the value of specific heat capacity at this stage or at this time will be lower as compared to before, because now it only has to do one job instead of doing two jobs as before. So how will you write this down? You will simply write down that there is no delta V, hence P delta V becomes equal to 0. To maintain same internal energy change, or to maintain or to keep constant, delta U equals to constant or fixed as compared to before. Less thermal energy is needed to do the same job. Now, since less thermal energy is needed, according to MC delta T, M and delta T are again constant or will be kept constant. So since Q is low, proportional C will also be lower this time around. And of course, don't forget to mention this equation in your answer while you're answering this question. Right? Okay. The next part is from simple harmonic motion. He says that this is an object. Okay, fine. It has a mass of 24 grams. Good enough. He says that it possesses this much amount of energy and travels a total distance of 14 millimeters. How is this 14 millimeters actually going to be visualized? You see, this object, while this oscillator is turned on or switched on, this object is going to move up and back down again. Move up, back down again. It's going to continue doing this. So if you visualize it as a wave, it looks something like this. And the total distance the object wants to cover or is going to cover is 14. So considering the mean position like this one, it goes up, comes down back again and goes back to the original position, covering a total distance of 14 millimeters. Now it becomes very evident and apparent that if I wanted to calculate the amplitude, it would just be this one, which will be 14 divided by 4, right? So this is journey 1, journey 2, journey 3, journey 4. So this comes out as 3.5 millimeters equals to x naught. The amplitude is 3.5 millimeters. Then he asks you calculate the angular frequency. No problem in that. We are going to use the energy and the angular frequency equation. So this becomes energy of oscillation is equal to half m omega square x naught square. And the equation comes from kinetic energy, which is half mv square, where v was equal to omega under root x naught square minus x square. When you take the square of velocity, omega gets squared and the under root gets cancelled out, so you're left with this equation. So the energy is 2.2 into 10 raised to the power minus 4 equals to 1 over 2. Mass is 24 grams converted into kg into omega square is what we want to find out, and x naught square, which is 3.5 into 10 raised to the power minus 3 whole square. So omega finally, of course, after taking under root and everything else, comes out as 38.6 radians per second. So this can be written down as 39 radians per second. The next point is the frequency of the oscillation is fixed. Okay, fine, which means that omega will not change and the amplitude of the oscillation is gradually increased. Okay, fine. It says calculate the maximum amplitude oscillation so that the object does not lose contact with the platform, which means that while this oscillation takes place, it should be increased, or it is increasing its speed so much so that there will come a time that the shelf moves upwards, the box moves upwards, but the shelf quickly returns back and the box does not have the time or enough time to react and come back down again because the shelf is moving so quickly, right? So he's asking you about that time. When will this box lose contact with the shelf? When the normal reaction will be 0. So in order to do that, we need to understand that the acceleration of the platform should either be less than or equal to the acceleration by gravity. Gravity should dominate, only then it will be maintaining a contact with the shelf. If the acceleration of the platform dominates, then it will lose contact. So in order to explore this extreme situation, since he does not want to lose contact, we are going to assume that they are both equal at best on the worst case scenario. So the acceleration due to simple harmonic motion comes out as omega square x naught, and acceleration of gravity comes out as simple g. So omega square from the previous part is 39 square, x naught is what we don't know because amplitude is required by us, equals to 9.81. So x naught comes out as 6.55 into 10 raised to the power minus 3 millimeters, which 6.6 into 10 raised to the power minus 3, which seems like a plausible answer because previously the amplitude is 3.5. So there could be a time that you increase the amplitude so much up to 6.6 that it eventually starts or wants to lose contact. Any faster than this, it will lose contact. Okay, so this is the logic. That is, you will write this down. Okay, the amplitude of oscillation is increased so that, and it is greater than B1. He says that whatever you calculated, it's going to be greater. Stated and explained the position of the oscillation where the first loses contact with the platform. No problem. As I discussed previously, there will come a time that the platform starts moving very violently up and down, and the box does not or will not or may not have a time to react to the gravitational attraction and may lose contact. If the contact has been lost, the normal reaction will be 0. So first we need to state when this is going to happen. At the top most position. Why? Because at that moment the platform will start moving downwards. It will start its downwards journey while the box may still be in the process of responding to the forces exerted by the shelf and by the weight of the object while it was moving upwards. It may not even have the time to react for that. So the topmost position will covers the state part. Now we'll have to explain that the acceleration of the gravity is less, right? The acceleration of the platform is greater than the acceleration of gravity, and it is not able to act, or you can say it's not able to respond in kind or as quickly as the shelf is moving. And at that time, the normal reaction becomes 0, right? The platform is still moving downwards, but the box may still be in mid-air, right? Okay. Question number 4. From capacitors, he says determine the total capacitance. These are in parallel, will be added together. This is in series, will be solved like a parallel circuit. So this will be 1 over C equals to 1 over 45 plus 1 over 10 plus 20 is 30. So after performing algebra, I can see that capacitor comes out as 18 microfarad. Do we need to include microfarad in these calculations? No, because everything is in microfarad. You can simply use them without microfarad and add micro at the end. So this is going to be 18 microfarads. He says a capacitor of 45 is connected with a power supply of 8. Its voltage increases to 9.6. What's the increase in energy? No issues whatsoever. So the equation goes something like this: half CV square, right? So you can do it in two ways. So this would be 1 over 2 into capacitance is 45 into 10 raised to the minus 6 into 9.6 whole square minus 1 over 2 into 45 into 10 raised to the minus 6 into 8 square. So that gives you the change, because increase or change requires a difference. Now you can quickly realize that this was one way of doing it, or you could just simply have taken the difference of the voltage square. So this could have been done in a single step as half 45 into 10 raised to the minus 6 into 9.6 square minus 8 square. And you can see that you can take this out, you can take the common out of this very easily. Please be advised that in these questions, 9.6 square minus 8 square is not equal to 9.6 minus 8 whole square. This is a basic maths error that you do. That's why I've written them down again. Please don't do this mistake. So if you have understood how to avoid this mistake, then the final answer of this whole scenario will come out as 6.3 into 10 raised to the power minus 4 joules, which you can write down over here. The next part he says to add a smoothing capacitor in the system. So the capacitor or the smoothing capacitor is always added in parallel to the load resistance if the output is coming from the bridge rectifier. To further understand this, you can check out my lecture on capacitors and smoothing capacitors to understand this, how this bridge rectification works. Basically, if this is our rectified output, then the smoothing capacitors actually convert this into a graph with less ripples or reduced ripples. This is a good idea for the appliance because it is not oscillating between an on and off position repeatedly. Rather, it is receiving, it feels like that the appliance is receiving a constant output with less ripples because of this capacitor, right? Now we have a rectified output. We know that the capacitor is connected because the outputs are smoothed out, right? It's a full bridge rectifier because we have both cycles being extracted outwards of the source. He says determine the time constant of the smoothing circuit. No problem. So for the capacitor, we have an equation in the syllabus that is V equals to V naught e raised to power minus t divided by RC. Now RC is my time constant. Okay, now since time constant is required, I will be taking tau instead of RC. So this equation turns to V equals to V naught e raised to power minus t divided by tau. Now t is of my choice. I will choose this t from the graph. And what does this t represent? That from V naught, after how long did it become V? Because we know that it is losing charge. How much time is it going to take to go from V naught to V? So now I go back to the graph and I choose V naught. It could be any value. It could be this one and then this one. This could be V naught and this could be V. It does not matter. But I will choose the obvious values because they are easy to pick. So my V naught in this situation becomes 4 and my V becomes this voltage value. It starts from this, ends its voltage at this point. How long did this action take place? So measuring the time from the axis will give me the value of t. This will be my V naught and the value it comes down to is my V. Again, I remind you, I could have selected two random points. I could have measured their time t, use this equation and you will get the same answer. I've tried this, you're going to get the same answer. So choosing the obvious options, we have 4 equals to 3.2, again picked from the graph, e raised to power minus t. Now you will notice that this time comes out as 8 seconds or 8 milliseconds. I'm not disturbing millisecond into seconds because my time constant is also already mentioned in milliseconds or already asked in milliseconds. I don't need to convert this. It won't serve any purpose to me. So 8 divided by tau. From this point onward, it's just a matter of logarithmic rules and algebra. So this will be 4 divided by 3. I've made a mistake. This will be the other way around. This is going to go something like this. This will be 4, the original voltage. This is the current voltage, which is 3.2. So this will be 3.2 divided by 4 equals to e raised to power minus 8 divided by tau. Taking log on both sides, this is going to become 3.2 divided by 4 equals to minus 8 divided by tau into natural log of e, which becomes 1. Now, this is a rule for natural log that if you divide a smaller number with a larger number, the log of this number will be negative. Now, since I'm expecting a negative answer for this, this is also a negative sign. It will get cancelled out. And the final answer that we get for tau or time constant comes out as 36 milliseconds. So this tau is 36 into 10 raised to the power minus 3. So this is 36 into 10 raised to the power minus 3. Or no need to write on myself because millisecond is already written. The sinusoidal output has a maximum power of 16 watts. Now this is an interesting question. This is the P max is equal to 16 watts. It says mean power, which is the another word for RMS power for the full wave rectified. Now this formula is exactly written in your syllabus, but if you don't understand this, we can find it out by calculating a simple formula that if I want to find out the RMS, I simply need to divide the P max with 2. But where do you get it from? You see, we understand that P RMS is equal to I RMS multiplied by V RMS. And we understand that it is I peak divided by under root 2 multiplied by V peak or maximum divided by under root 2. Simple mathematics leads to this idea that it is I peak multiplied by V peak divided by 2. This under root 2 multiplied by under root 2 becomes 2. Now I peak and V peak is actually my maximum power, right? P max. What's the absolute best? So automatically this formula becomes P max divided by 2. So since it's a state question, no explanation is needed. 1 mark question, I simply should have divided this with 2 and this answer will become 8.0 watts. The next step is half wave rectified. Now, half wave rectified power output is not discussed in the classrooms generally, which means that the examiner relies on this idea that you will be able to calculate this based on intuition, based on your own understanding of the system or this question. You see, if the full wave rectified output in which all things are extracted is giving you half of the original power, which is 8 watts, then a half wave rectified system in which half of the wave is not extracted, this energy was not extracted, this energy was not available, how much damage would this do? How much energy will this be losing? This would even be half of the full wave rectifier. If the full wave is providing 8 watts, then half wave should be providing even half of that. So the RMS power of this should have been 4.0. But if this does not look good to you, if you don't understand this, again, it's not part of the course. You can go back online and you can research that how this RMS value is calculated. For a full wave rectifier, we understand that it is always 1 over under root 2. But for a half wave rectifier, it is actually half of the same 1 over under root 2 factor. That is why the intuition or the guess that you did that it is going to be half of the full rectifier was actually correct. You can check online that for full wave and half wave, these are the equations. Okay. All right. Next, question 5. He says that there is an object moving in a circular constant speed, which two quantities will be varying. So in circular motion, what quantities keep varying? So that is the velocity. Velocity keeps varying. It's the acceleration keeps varying because it is always pointing to the center. Its vector keeps changing. The value does not change. And as a result, the resultant force also keeps changing. Why? Because it equals to ma. And if A is changing, the whole quantity is changing effectively. Right? And another question that will be momentum. Another option. Because momentum is mass into velocity. Since velocity is changing, the momentum is also changing. A charged particle of mass m charge q enters a magnetic field. He says perpendicular. Okay, fine. The magnetic flux is B. He says it travels in a circle, period T, radius R. Again, as I mentioned earlier, this question actually stems from the geostationary question from the gravitational question. I don't particularly like these questions, but what can we do now? Okay, so since I have to prove this, it looks like that the magnetic force is equal to the centripetal force, or another way of saying this will be that the magnetic force provides the necessary centripetal force so that object can move in a circular direction or in a circular path. So the magnetic force comes out for a single charge as QVB. And for the centripetal force, we have two formulas. We can either use mv square over r or we can use mr omega square. Now I see the time period and I am inclined towards using this equation. But when you use mr omega square, you will soon realize that cancelling out the square becomes a problem later. So it's better right now to use this equation. You can do this by hit and trial method, okay? So V gets cancelled out with this V, right? And since B has to be subject to the formula, I keep B over here. I take mV divided by QR. All right? Okay. Now, then we have an equation for velocity which is equal to R omega. Right, let's replace that in this V. So this equation becomes B equals to M into R omega divided by QR. Right, so this R cancels out with this one. We are left with M omega divided by Q. Now we know that omega is equal to 2 pi by T. Let's replace that over here and we are left with 2 pi M divided by QT equals to B. So we've successfully shown this equation what the examiner wanted. Again, if you're unable to solve this, use this equation for the next part. It says for an alpha particle, time period of this, calculate B. So we're going to use this equation. B equals to 2 pi M divided by QT. That is QT. So 2 pi comes as it is. But how much is the mass of the alpha particle? So the alpha particle is 4,2. It has 4 nucleons. So 4 multiplied by atomic mass unit, which is 1.66 into 10 to the power minus 27 kg given in the data booklet, divided by charge on the alpha particle, which is 2 positive charges. So 2 into 1.6 into 10 raised to the power minus 19, that is the elementary charge. Time period is 2.5 minus 6, so this is 2.5 into 10 raised to the power minus 6. When you calculate this using the calculator, the final answer comes out as 52 into 10 raised to the power minus 3, so this is 52 millitesla of the magnetic field strength. A second alpha particle as a uniform field has a radius 2r. Say it and explain how the periods depend. Now notice that because of this equation, does magnetic field depend on radius? Is there a codependency between them? No. B is independent of R. There is no variable of R in this equation. So we will say that there is no change in radius or no change in the motion, except one thing, we'll get to that later. So there is no change as B is independent or does not depend on R or the radius. But there is one thing that is going to be different. What's that? You see, this is the center of the circle, and let's say this is the alpha particle previously at a radius of R. There is a new particle at this point that is moving like this, which is at a distance of 2R. Now, if the time period is same, for example, same uniform magnetic field, circle of 2R, right? Explain how the periods of the motion is going to change. You see, the period does not depend on the radius, which means that the circular velocity, or you can say that the angular velocity, omega of this and omega of this, will be exactly the same. Now, the tangential velocity, which is at 90 degrees, is equal to r omega. Now, since omega for both of them is same, because changing the distance of radius has no effect on the period, right? So, if omega is not changing, then v is proportional to r. And if r increases, the velocity increases, so that this curved object can keep up with this one at same angles throughout its journey. So the outer one has to move a bit faster, right? So we can say that the velocity or the tangential velocity of alpha at 2r is greater than alpha at r. Okay. All right. And we can see that time period has no relationship with radius. There is no t in this equation. Everything is constant, right? All right. The speed of the alpha particle is this. An electric field is applied so that the particle now moves at a constant velocity. Okay, no problem. Use your answer in B2 to find out the field strength. So again, we can say that the magnetic force Fm is equal to the electric force. The magnetic force comes out as QVB equals to the magnetic electric force, which is QE. Okay, and Q gets cancelled out. We are required to find E, so E is equal to the velocity, which is 1.1 power 6, 1.1 power 6 into B, magnetic field density, that is 52 power minus 3. So this is 52 into 10 raised to the power minus 3. Electric field strength comes out as 57.4 into 10 raised to the power 3 Newton per coulomb or volts per meter. You have two units for this. So this is 57.4 into 10 raised to the power positive 3 with a unit of Newton per coulomb or volts minus 1. Moving on to the second part of this video, that is starting from question number 6. We have 64 turns, highlighting this first. Cross-sectional area given centimeter square, we need to convert this to meter square. And there is a small coil placed inside a larger coil. So all the details, or all these details are given for this coil, that is a smaller coil placed at the center. Okay, so be advised, right? Okay, so this is 64, this is this one. Let's zoom in a bit. All right. So then he says that there is a constant current in the solenoid. Where is this current? This is the current. Now when the current passes through this coil, it acts like a bar magnet, and that bar magnet influences this coil, and it will cause an induced EMF on the coil, right? Okay, sketch a line. He says it's moved through the solenoid from position X to Y Okay, fine. Variation in the magnetic flux linkage. Now, what's the formula for that? So magnetic flux is simply BA. If you want to find out magnetic flux linkage, you have to multiply the number of turns with the same formula. That becomes linkage, right? So is there any change in the value of current? No. So from previous knowledge, we understand that the magnetic flux density of a coil depends on the current, okay? If you provide more current, it is going to become a stronger magnet. But since the current is constant, the value of B is not changing. Is the cross-sectional area of this coil changing? No, it's not changing. Have the number of turns of this coil changed? No. So all of these quantities physically are constant. They are not changing. So the flux linkage will be a constant value while moving from X up to Y. Does not change. He says explains the same thing that you've talked about. Explain the shape. So first you will write down that the flux linkage, or the formula for flux linkage, is NAB. You will mention that N is constant. You will mention that cross-sectional area is constant. Then you will discuss why B is constant, because B depends on current in solenoid or coil. Since the current is constant, B also constant, hence the flux linkage, or the complete formula for NAB, is constant, right? So there are two physical limitations, N and A, and one electrical limitation, that the current is not increasing or decreasing. Then there is nothing is going to happen. So in this part, he says that coil C is now held stationary, right? That is stationary, and coil X is also stationary. So they are not moving. There is no relative motion between them. Whatever is happening in coil C will be reflected on coil X. So this is coil C, for example. For this, we have the graph represented, and coil X is somewhere in the center over here represented, right? But they're not moving. They have no relative motion with respect to each other. So it says that the solenoid varies a magnetic field with density B as shown in the figure. He says calculate the maximum magnetic flux linkage. Now, the maximum magnetic flux linkage is phi equals to BAN, right? And for the cross-sectional area, we do definitely have a value in the previous part as 0.71, and the number of turns are 64. So 0.71 will be the cross-sectional area divided by 100 square to convert it into meter square, and then we have the number of turns as 64, right? And the maximum, since he's asking about maximum magnetic flux density or magnetic flux linkage, we'll have to choose a value of B to be maximum. So the maximum value of B is 0.080. So this is 0.08, and when you finally calculate this, this comes out as 3.6 into 10 raised to power minus 4 Webers. So 3.6 into 10 raised to power minus 4. This is an interesting question. He says that now make the graph for an induced EMF in coil C. You see, when you're providing this current in this coil, it has its own magnetic field. Let's say this is north and this is south. This effectively looks like a bar magnet. Now this magnetic field influences this coil that is placed at the center. And we know, according to Faraday's law, if you change the magnetic field of a conductor or around a conductor, that conductor experiences an EMF. So it's all about this coil C experiencing the voltages now. Now notice that up to T, is the magnetic flux linkage changing? Is the magnetic flux or magnetic flux density changing? No, there is no change. So according to Faraday's law, EMF will only be introduced if there is a change of flux divided by change in time. That means that there should be a change in the value of BA. Now, can you change the cross-sectional area at all times? You can't do that. So effectively, EMF basically depends on the value of changing value of B. This is what he wants to do, right? With respect to time. So is the value of B changing in this region? No, it's not. So at that point, there will be no EMF. So I will have a 0 value of EMF. Next stage, the value changes. There is a change in magnetic field. So of course, there is going to be an induced EMF for a time period of 0 to 2t. For the sake of example, I consider that this is, let's say, 1 box. So up to 0 to 2t, this is going to 1 box. It's my choice because I don't have to calculate this. I can do this on my own, right? So this is the first stage. What happens at 2t? So at 2t, it starts changing in the opposite direction. Now, from the Faraday's law and Lenz's law, we understand that EMF is proportional to flux, change in flux divided by time. But according to Lenz's law, we had a negative sign, that it's going to be in the opposite direction. Right now, if the gradient was positive, and for the sake of example, you gave a positive EMF, this time, if the gradient is now negative, you should change the EMF as well. Now, getting even more technical than this, if the gradient is positive, then my EMF should be negative. EMF should be negative, right? It should be a negative EMF. Why? Because according to the formula, if the gradient is positive, the positive multiplied by negative gives me a negative EMF. Today, however, the gradient is negative, so phi becomes negative. So negative multiplied by negative gives me a positive EMF. So now I will be existing in the positive region. But how much should I make the value now? You see, it is always with respect to change, with respect to time. If you calculate for this one, it changes from 0.04 to 0.08 in a time of, let's say, t. From 2t to t, there's a time of t. What happens in this region? It changes from a 0.08 goes to 0. So 0.08 minus 0 divided by how much time has it taken? So from 2t up to 4t, a total of 2t. So this is 2t. When you simplify this, you realize that this is going to be 0.04 divided by t, this one. This one also comes out as 0.04 divided by t. So primarily, the change in fluxes is same. So induced EMF will also be same, which means that this time, if I chose one box for the EMF, I will choose one box for the other side as well and go up to 40. Now I will remove this because we don't know what happened after this. We don't know what's happening after this, so we can't conclude that it comes back to 0. So I have to leave it at this point. Okay? All right. The part B deals with this coil, and for this question, you have to go back to O levels and you have to revise a few concepts to understand this point. If you remember, you used to do the right hand grip rule. This is the right hand grip rule, that the direction of the thumb for a wire shows the direction of current and the curl of the finger shows the direction of magnetic field, right? Now, when two parallel wires carrying the current in the same direction are placed in very close proximity to each other, they attract each other as mentioned over here. And why is that so? Because of their magnetic field that is around them. So in this one, the magnetic field goes like this, right? And the other conductor, the magnetic field goes something like this, again using the right hand grip rule in this configuration. We notice that the resultant magnetic field at the center, because of the first conductor says up, the second conductor says down, so the magnetic field at the center is weak. But on the outer side, we experience that the magnetic field is exactly the same. So this goes down and it tries to complete a loop like this. So the magnetic field on the outer side is strong. Now in physics, force is always exerted from an area of strong region towards an area of weak region. So from strong to weak, from strong to weak. So these wires effectively are getting attracted towards each other when they're carrying current in the same direction. This is important. Now, are they carrying current in the same direction? So if you draw this coil in 3 dimensions like this one, you will see that this is what it looks like. The turns are coming from the front, going to the back, coming from the front, going to the back. Now, if you notice that for the conductors carrying current from the front, the direction of current is the same. They're carrying current in the same direction. Now, we understand that 2 parallel conductors carrying current in the same direction experience an attraction. Now, when they experience an attraction, these coils will be attracted towards each other. This is the reason for attraction among the coils. So what's going to happen to this coil? The loops are going to get attracted towards each other and the coil will shrink. The distance between these coils will decrease. So how will you mention this? You will say that there is a current in the coil. What does it do? Produces a magnetic field that is circular. Or you can say using the right hand grip rule, we figure out that the magnetic field interact and cause attraction force between loops. Now, since the question was that explain what you see, right? Describe and explain the change in distance between the turns. The distance between the turns. So we explained for 2 marks why this is happening, and now we explain what we observe. So the distance between loops decreases, or you can say that it shrinks, or the loop start coming close to each other like this, as opposed to the one given in the question. So I hope that we understand that this is a refresher course for at least one topic of O levels as well. Okay, question number 7. He says a photon has this energy, and I understand photon energy formula are these two. He says calculate the momentum of the photon. This formula is directly mentioned in your syllabus, and that goes something like this: P equals to E divided by C. So simply the energy, that is 3.11 into 10 raised to the power minus 19 divided by speed of light, which is 3 into 10 raised to the power 8. The momentum comes out as 1.04 into 10 raised to the power minus 27. Notice that this is 3 significant figures, so I am writing my answers as 3 significant figures. It says the beam has 350 milliwatts, has this wavelength, and the photons are emitted, or the number of photons emitted in 1 second. How to do this? There are 2 methods to do this. First is going to be a unitary method. The second one is going to be a straightforward question. First, we find out how much energy does 1 photon possesses out of 640 nanometers. So E is equal to hc by lambda. So this is going to be 6.63 10 to the power minus 34 multiplied by speed of light, which is 3 into 10 to the power 8 divided by 640 into 10 raised to the power minus 9. So the energy of 1 photon comes out as 3.11 into 10 raised to the power minus 19 joules. How much power do you need in 1 second? So power is equal to energy divided by time. So since time is 1 second, power effectively becomes energy. So I need 350 millijoules of energy from the laser, right? This value is exactly the same as energy now. Or you can take this equal to 1, multiply this over there, and get the same answer. So from this point onwards, we realize that this is what we want. This is the energy by 1 photon. So it's a matter of ratio method, or you can simply see that this is 350 into 10 raised to the power minus 3 joules needed divided by how much one of them is providing, 3.11 power minus 19 joules. So when you do that, it comes out as 1.13 into 10 raised to the power 18 photons. So I need this many number of photons received in 1 second so that my laser can generate this much amount of power. Okay, all right. So write this down over here. He said the laser beam is incident normally on the surface, absorb all the photons, show that the force exerted by the surface of the laser is this, or given by this, no problem. So this is momentum equals to E divided by C, right? And we understand that power is equal to energy divided by time. Okay, so let's replace, in place of E, we have P multiplied by T equals to E. Let's replace that over here. So this becomes momentum is equal to power multiplied by time divided by C, right? And when we have force, that is equal to change in momentum by time, right? So from this idea, we can replace momentum in this position, or over here, we get force is equal to Pt divided by C divided by T. So this T gets cancelled out with this one, and we are left with P divided by C, which is equal to force. So we have successfully shown this formula as well, right? Okay, moving on to the next part. He says light of single wavelength is this one. The work functions are given to you. The energy is given to us. Okay, fine. Explain the term threshold wavelength. A threshold wavelength is the maximum possible wavelength. Why? Because E is equal to hc by lambda. If you want to make sure that the work function takes place, right? So we need to look at it from this perspective. Generally, we used to say that it is a minimum frequency required, right? So if the minimum frequency required, we know that frequency is proportional to wavelength. If in general definition we say minimum frequency required to eject an electron, then in terms of lambda, in terms of wavelength, it will be referred as maximum wavelength. So it's just a matter of reversing the English for this. So this will be maximum wavelength because we understand that increasing the wavelength decreases the energy, right? So how far away, how much lambda can we increase that the energy reduces so much that these ejections do not take place, right? So that is what we're looking for. So maximum wavelength that can cause emission of what? Emission of electron from where? From metal surface. That is a photoelectric effect. Okay. From the table of metals, calculate the largest threshold wavelength to do so. So that will be E equals to hc by lambda. If I need the larger threshold, then I need the smallest energy. So from the table, I pick out the smallest energy of potassium 2.26. So this goes something like this. So 2.26 into 1.6 into 10 to the power minus 19 bracket closed equals to 6.63 into 10 to the power minus 34. Speed of light 3 into 10 to the power 8 divided by lambda. Lambda comes out as 550 into 10 to the power minus 9. So this is 550 into 10 to the power minus 9. Now, if you do the same question by changing this value of 2.26 and replace 4.49, 3.6 and 2.26 again, you will realize that the wavelengths come out something like this. So this was 550 nanometers. This comes out as 338 nanometers. This one is 277 nanometers. So we can see that the largest wavelength was found for the smallest energy, right? So we've done the question correctly. We'll go towards question number 8. He says, state what is meant by binding energy of the nucleus. So binding energy is the the minimum energy. The minimum energy needed to break apart a nucleus. And separate its nucleons up to an infinite distance. Why do we say that they have to be separated to infinite distance? Because if the nucleons, we suspect that if they come close together, they might undergo fusion and make a nucleus again. We are not looking to make a nucleus. We're looking to separate them. We're looking to break them apart. So the distance between them is infinite. It increases so much that there is no chance of them coming close back again and becoming a nucleus again. So we want to eliminate that chance. That's why we say that they go up to an infinite distance, separated up to infinite distance. Now he says that the number of neutrons, no problem. So neutron is N10. So equation for the lower side will have no meaning to us because the neutrons get multiplied by 0. So we're going to make an equation for this system from the atomic number. So this is going to be 235 plus 1. The arrow represents the equal sign for simple algebra. And I'm considering the values from the top values. So this is going to be 142 for xenon plus 90 for strontium plus x into 1. This one, x multiplied by 1. So this x comes out as 4. So I have 4 neutrons as the output. So this will be 4 into N10. He says that these are the binding energies per nucleons given to you. Okay, fine. He says how much energy is released in megaelectron volts as fission of one nucleus. You see, Einstein told us that the system's mass and energy remains conserved. If you can't see mass, then you will see energy, right? So in order to do this, we're going to first calculate the energy. So this is going to be multiplied with 235 as nucleons, multiply this with 142, multiply this with 90. You will find out that these answers come out something like this. So this is a 1783 mega electron volts. I'm ignoring the decimal places now because I want to explain the question. This comes out as 188 mega electron volts. This comes out as 784 mega electron volt. Now, these are all energies, right? So either I represent their mass or I represent their energy. I'm talking about the same thing because according to E equals to mc squared, they are both representative of one another. So either I write down this energy or either write down mass, they're exactly the same, right? So the energy of uranium before the system, before everything happened, comes out as 1783. After the reaction, they possess this much amount of energy, 1188 and 784. I will take the difference of energies and see which one is greater, which one is lower. So naturally what happens is that when the energy of uranium is subtracted from a xenon and strontium, so this is 1783 minus 1188 plus 784, right? So this comes out as a negative of 189.69 mega electron volts. What happened? Where is this extra energy coming from? Where is this extra energy missing from? So basically what happened was that this reaction also releases energy, and that energy is represented in terms of this difference, which is 189 mega electron volts, MeV, right? And can this be converted into mass? Yes, by using E equals to mc squared. I put this over here. We can find out the change in mass after the fission of just one atom of uranium, right? So energy is released in the process. So how much energy is released? 189 mega electron volts. Okay. All right. Moving on to the next part, we have the isotope of xenon is 142 and is unstable. The isotope xenon 132 is stable. Suggest a reason why xenon 142 is unstable. You see, we can see that there are more number of neutrons in comparison to this one. This is something that is not a part of your course, but again, based on your previous knowledge that you've already done in A levels, you can simply predict that there are too many neutrons, hence it is unstable. This would have been a good answer. But for the sake of proper understanding, or the sake of full understanding of the syllabus or the chapter at least, there is something called neutron to proton ratio for stability, and it has to be less than or equal to 1.58 generally in real life, which means that the number of protons ideally should be equal to the number of protons. This is the ideal combination. But at best, or on a worst day, the number of neutrons equal to 1.6 times the number of protons. Although number of neutrons have to be greater than protons to maintain stability, but they shouldn't exceed this ratio. We can see very clearly that in xenon 142, if you go to the periodic table and figure out all the values, the ratio for xenon 142 is actually 1.6. And for 132, it is actually 1.4. So by simple general physics, since this 1.4 is less than 1.58, it will be stable. And since 1.6 is greater than 1.58, it will be unstable. But I understand you're not supposed to know this information. You're not supposed to memorize this because it's not a part of your course. What is a part of your course is simply recognizing that there are too many number of neutrons and it will cause instability. Does that happen? Yes, it does. What is happening over here? Uranium was made unstable by adding a neutron. That is what leads to the nuclear fission reaction. That is what leads to power plant's energy, right? Okay. Next we have, he says that xenon decays to become isotope of cesium 142. He says that sample initially contains only this one. So let's say that the original or the standard number of atoms is this. N naught is the original atoms. Let's say that these were 1000 atoms. Okay. All right. He says they decay to become cesium. After a time of 6 seconds, the ratio becomes 31. What is this ratio? So let's consider this undecayed, the ones that did not decay. Let's consider to be N. Let's say that 200 atoms have decayed. So this will be 200. And undecayed will be 800, as 1000 minus 200 will be 800. So how many have decayed? So decayed will be 200. I'm just putting these values for a reference. Okay, no need to worry about that. So decay, to find decayed number of atoms, I'll have to take this n naught minus n. If this is n and this is n naught, the decayed atoms will simply be calculated by taking the difference, right? So for a decayed, for the number of atoms that have decayed, I will use the equation n naught minus n divided by the undecayed, which did not even participate, which haven't even decayed now, will be n as this one, right? This is equal to 31. So then it's simple algebra. So this is n naught minus n equals to 31, multiply by n, take this over there. This becomes n naught equals to 32 times n, which means that n over n naught is equal to 1 over 32. If you take the cross multiplication, then this is what happens. N naught over there and 32 over there. This is what you're left with. Okay. So the equation of decay goes something like this, that n is equal to n naught e raised to power minus lambda t. So this is n divided by n naught equals to e raised to power minus lambda t. Okay, fine. So do we have an n over n naught? Yes, we have. That is 1 over 32. So this is 1 divided by 32 equals to e raised to power minus lambda t. And from this point onwards, it's a matter of taking logarithm, right? So this is ln of 1 divided by 32 equals to negative lambda t and ln of e. So when you calculate all of this, this is going to come out as minus 3.465 equals to minus lambda and a time frame of 6 seconds, because this is mentioned in the question that this happened after 6 seconds. So this t will be 6. ln e becomes 1. It vanishes after getting multiplied. So what are we left with? Lambda equals to this divided by this, and negative sign cancels out. So lambda comes out as 0.577 per second. Since we're dealing with time in seconds, this will be in per second. So then we have an equation from the syllabus that T half-life is actually equal to ln of 2 divided by lambda. So 0.693 ln 2 divided by 0.577 gives me an answer of 1.2 seconds. So this is 1.2 seconds. Now if you go online on Wikipedia, you can check that xenon 142, if decays to become cesium 142, the half-life is approximately 1.22 seconds, right? So I've just added this because we don't have a marking scheme right now on our hands. I'm adding this information from the Wikipedia that this question answer is absolutely correct. Okay, all right. Question number 9, he says electrons in vacuum are accelerated to make X-rays with a potential difference of 84 kilovolts. He says minimum wavelength. This equation again is mentioned in your syllabus, directly in your syllabus, and that goes something like this, that the energy of the photon, for example, which is HF or Hc by lambda, is equal to the energy of electron that is going to be accelerated towards the metal target. So this is 6.63 into 10 raised to power minus 34 into C in 3 into 10 raised to power 8 divided by lambda is what we are looking for, equals to charge, which is 1.6 into 10 raised to power minus 19 of an electron. Voltage is 84 kilovolts, which is going to be 84,000 volts. Finding lambda out of this gives us 1.48 into 10 raised to power minus 11, which generally does lie in the range of X-ray. Next we have, he says that the target metal for the X-ray can be made out of copper or tungsten. Which one would you choose? You see, we understand that this process actually heats up the metal to a very high value. We want to avoid the metals from melting, so we will be choosing tungsten for this process because of its high melting point, and because due to these X-rays, the metal or the target metal heats up very quickly. So it gives us a very high headroom to experiment or to run the X-ray machine for a longer time, because we know that it will not be melting because there is a very large room still available for the heating process to still continue or the X-ray machine to be used still. So you can write this down in English over here, right? That the kinetic energy is converted into thermal energy of the electrons, and since tungsten has a higher MP, it is under low risk under low risk, or there is a low chance of this ever actually melting. All right. Okay, so X-ray beam, we have soft tissue and bone. Data for the two materials given at 9.2. This is that data. Okay. So acoustic impedance are given. So he says that the incident X-ray beam and the transmitted intensity, which means that he is going to eventually talk about the transmission coefficient. Not now, but eventually. And 13% of incident is actually transmitted. So the equation goes I equals to I naught a raised to power minus mu x. And there will be a compounding effect if there are more than one mediums. So of course we understand that there is bone and then there is flesh. So I divided by I naught is represented 13%. So this is actually 0.13 equals to a raised to power minus mu, which is 0.22. And x is given to us as the thickness. We don't know the total thickness right now. So this is x multiplied by the compounding of the next medium, that is going to be minus 3 into x. Okay. All right. So and x is taken because for soft tissue it's x and for bone is also x, right? So when you solve this algebraically, this is going to become e raised to the power minus 3.22x. Bases are same, the powers will be added together, equals to 0.13. Okay, then it's a matter of taking log or natural log on both sides, replacing everything, and then the x comes out as 0.633 centimeters, because the whole question was moving in terms of centimeters, if you can notice. Okay, so this is 0.63 or 633. Define the specific. Now we understand that acoustic impedance is actually equal to the density multiplied by the speed of ultrasound in that medium. So simply explain this. It's the product of density of that medium with the speed of ultrasound in that medium. He says use table 9.2 to find out the transmitted intensity at the boundary between soft tissue and bone. So the formula goes something like this, that if this was our original intensity I naught, there will be a transmitted intensity and there will be a reflected intensity bouncing off from the boundary. So the formula that we have is IR divided by I naught equals to alpha, which is the reflection coefficient, equals to bracket Z1 minus Z2 divided by Z1 plus Z2 whole square, which is going to become, or values are going to be taken from this. Now since all of them are 10 power 6, I don't have to write them down completely. 1.7 and 7.8. So this will be simply 1.7 minus 7.8 divided by 1.7 plus 7.8 whole square. So this IR divided by I naught comes out as 0.412. What does that mean? It means that if 100% intensity was sent in, then 41% is reflected back, because this is for reflection. So how much is actually transmitted? Simply 100% minus 42% or 41%. So we are left with 59%. This is 41%, right? So we are left with 59. So this is percentage. So this will be 59. If this had been a fraction, this would be 0.59. So this is 0.59 or 59% is transmitted in, 41% reflected back. He says, suggest two reasons why transmitted intensity through the sample is less than the answer in C1. No problem. He says that, why is that so? Why is this energy less as compared to what we are calculating? You see, there are multiple reasons for that. So there is going to be some ultrasound that is absorbed or attenuates. Attenuates mean loss of energy. Attenuates while moving through medium. Right? Next, some ultrasound is reflected back. Reflected ultrasound reduces intensity of the final product. Right? And it reflects back all the other intensities as it encounters more boundaries. You see, at this point, what's going to happen? First, it gets reflected back from this location, then transmitted from this location, then the transmitted wave bounces back from this location, then bounces back from this location. So every time it encounters a boundary, it reflects back a certain portion of that wave. So it's very highly unlikely that a lot of ultrasound is actually going in to begin with. So last question, we have a question number 10, that is, the sun has a surface temperature of this, luminosity is this, radius of the sun. So it's a very simple, straightforward formula, that is, luminosity is equal to 4 pi r square sigma T4, right? So this becomes 3.85 10 raised to power 26 equals to 4 pi into r square into sigma is given in data booklet as 5.76 into 10 raised to power minus 8 into T4, which is 5780 power 4. Please don't forget to take the powers. These are important. This is r square, this is 4. So r finally comes out as 6.96 into 10 raised to power 8 meters. Write this down over here. The earth has a distance of this one from the sun. Calculate radiant flux density, no problem. This is the sun, this is the earth, and this is the distance between them, which is 1.5 power 11. So flux intensity goes something like this. So this is F equals to L divided by 4 pi d squared. So this is going to be 3.85 into 10 raised to power 26 divided by 4 pi d square, which is 1.5 into 10 raised to power 11 whole square. Don't forget to take the d square or the square of this equation. So this F comes out as 61 watts per meter square, which will be 1360 watts per meter square. And this is a reasonable estimate because when you take solar panels and you take solar energy into consideration, you will notice that they actually calculate with 1000 watts per meter square. So what happens is that if this is the ozone layer and this is the Earth's surface, we are receiving approximately 1400 watts per meter square from the Earth, from the sun. And what gets filtered out from the ozone layer gets down to 1000 watts per meter square. So yes, this value is a reasonable estimate. The next question is from the Wien's displacement law, which goes something like this. So lambda max multiplied by the temperature of the surface equals to a constant value. This is the Wien's displacement law. Right now, the maximum lambda max of this current situation is this one. This is the maximum wavelength. Okay. He says that draw the graph of the sun but at a lower surface temperature. What would happen in this situation? As you can see from the notes of the book, that if you decrease the temperature, the graph becomes less and less flat. Plus, the value of the peak gets shifted forward. So this was, let's say, this one, then this is 500, and the even cooler ones will have a 725. So most likely the graph would have gone something like this at a cooler temperature, where the lambda max of that scenario is higher than the previous situation, than the previous case. It stays beneath the first graph, right? And it is a bit less. Its peaks are less. Okay. So this is the answer for this question. And this is the diagram taken from the book. Then we have the name of a star. He says it's moving away from the Earth with a certain reference. He says that the sun, our own sun, produces this effect. This is the visible spectrum. Now, these wavelengths are already mentioned. This is 397. This is 410. This is 434. This is 486. And this is 656. This is what we already know from the examiner's perspective. This is what our sun does. And we expect the same behavior from other suns or other stars away from us as well. He says that since the galaxy is moving away from the observed Earth, calculations are not required. Tell us where these wavelengths will go. This phenomena was referred to as redshift, and it is caused by the Doppler effect, right? You can go about and read about this and study the book about this, but I've added an image from the book that the wavelengths are actually shifted forward, closer to red, right? And the Doppler effect suggests that if the object is moving away from you, the frequency decreases And since we know that the wavelength is opposite to this, the wavelength increases. So that is how we got to know that all the objects around us are actually moving away from us. Our own sun produces this pattern, and all the stars in the galaxy should produce the same pattern, but they're not. Their wavelengths appear to be slightly shifted, which means that they are undergoing the Doppler effect, and their wavelengths are higher than perception. And if their wavelengths are higher, their frequency is lower. And if the frequency is lower, that means that the objects or the galaxies are moving away from us. This gave us the guarantee about the expansion of the universe, that the universe is expanding, because every star I look at, this is what it does to me, right? So that means that universe is ever expanding. We are moving away from each other. So we simply had to draw these wavelengths, but at a larger distances. No calculations required. So this probably would be at 500. This over here, and then over here. Notice that I have shifted this forward, shifted this forward, shifted this one forward. Similarly, so on and so forth. This is what you're required to do. Okay. All right. Last part, he says, it's moving, that star, the galaxy moving at this speed. Use your information in B1, be that anyone. Calculate the wavelength of the lowest visible energy. Lowest visible energy means that this should be, if the energy is low, then the wavelength should be highest, or the higher one. So I will be choosing 656 for my calculations, right? And the formula goes something like this. The change in a frequency, or the change in wavelength divided by wavelength, is approximately equal to the velocity divided by the speed of light, right? This is also another formula given in the question for Doppler effect. So delta lambda is what we want to find out, equals to the speed of the galaxy is 244. This is what was given. So 214,000 into 10 raised to power 3, because this is kilometers per second, and the speed of light, we remember, is in meter per second. This lambda goes over there, gets multiplied, so this is 656 nanometers. So the change in wavelength comes out as 46.8. So 46.8 nanometers change is observed. Should it be added or should it be subtracted? We understand that the wavelengths are actually increasing. So 656 plus 46 will give me 702.8 nanometers. So this will be 702 or 703 or 700. We'll go to look at the marking scheme to confirm this. Okay. Last part, he says, it's a good question. He says the calculation does not give an accurate value. Used value for the surface temperature of the star. Okay. The wavelength is used to calculate. State and explain whether the value of temperature is too high or too low. You see, from the Wien's displacement law, we understand the lambda max multiplied by T is equal to a constant, right? This is what we already know. So if the wavelength perceived by us has now increased, and it has to be a constant according to the displacement law, then the value of temperature calculated will be too low, because the true answer is 656, but we're getting 702 or 703. So due to this false reading of larger wavelength, I will be getting a false reading of smaller temperature. This is what he's asking you. That answer is too high or too low. So our answer is too low. And we explain it with reference to the Wien's displacement law. Right? Okay.